Welcome to the lecture. You may recall that in the earlier lectures we had considered the setup of multiple linear regression model, and we discussed different types of aspects related to the fitting of model, judging the goodness of it of a model, and finally the objective was to get a good fitted model. Now let us take a simple example to understand whatever we have done in the earlier lectures, right. So if you see here, I am going to consider here an example where I am considering 27 observations, and these observations have been obtained on the demand of drinking water, which is measured in thousands kiloliter, and we believe that this demand depends on the temperature, that is the weather temperature and humidity level. You may also recall that in the case of linear regression model, we also considered a similar example in which I had taken only one variable, that is temperature, and now I am going to consider the second variable as a humidity level, and that is measured in percentage. So the model in which we are interested now here is y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus epsilon, and we have got 27 observations. So I can express the model as yi is equal to beta 0 plus beta 1 xi 1 plus beta 2 xi 2 plus epsilon I. Okay. Now first let me explain how these things can be expressed in the framework of a multiple linear regression model. So here the model which we had considered was expressed as y is equal to x beta plus epsilon, where y was a n cross 1 vector of observations on response variable, and x was a matrix of order n by k of k independent variable having n observation on each of the variable, and beta was a k cross 1 vector of regression coefficients, and epsilon was a n cross 1 vector of random error components. So now in this case you can see that here n is equal to 27 and k is equal to here actually 3 including the intercept term. Okay. So now I can express all the 27 observations on y here like this, which is a 27 cross 1 vector. And there are two variables x1 and x2 on which we have got 27 observations, and all these observations including the intercept term can be expressed as a matrix X which is of order 27 by 3. And similarly beta contains 3 elements. First is intercept term and other two are slope parameters. Beta 1 is the slope parameter associated with x1 and beta 2 is the slope parameter associated with x2. Now let us try to use a software which can analyze this data. So as discussed earlier, we had seen that there are different types of statistical software available, and some are paid software and some are free software. Among the paid softwares, MINITAB, SysStat, SPSS, SAS, and all such softwares are quite popular. And among the free softwares, R or Gretel, these are two popular softwares among others, right. So in this lecture, we are going to use the software MINITAB, but definitely if you use any other software, that will also give you the same outcome. There can be some difference in the format, that some software may give ANOVA table first and then the regression coefficient, and some software may give the regression coefficient first and then the ANOVA table, so and so on. So there are only minor differences among the outcome of a software, so that doesn't make any difference. Now before we go forward, let me explain you what is our objective. My objective is not to find a model here. My objective is that first we try to expose this data set to a software, and whatever is the outcome of a software, we have to understand that thing. So, the first question is this: what different numerical values are indicating and how they have been computed, and they correspond to which of the quantity that we have covered in the lecture. And after that, we will try to analyze all the things one by one, and finally we will try to combine all our outcomes together, and then we will have a final fitted multiple linear regression model. Right. Okay. So, let us now start with this thing, and I already have entered the data in this MINITAB software. So, you can see here that in the first column I have entered the data of drinking water demand, the second column has the temperature, and third column has the humidity. Now, first of all, we have to ensure that can we really use here a multiple linear regression model. So, we try to plot them. Since this is a multiple linear model, so we would like to go for multiple scatter diagram, or in the case of MINITAB, this is called as matrix plot, right. So, now there are different options available for the matrix plot, and then we are just going to opt for a simple matrix plot. And we can see that here I have chosen here all the three variables C1, C2, C3, and once I try to plot it, I get here a scatter diagram like this one. Okay, let us try to first leave it aside and try to make some other things, and at the end I will try to copy all the commands, and then we will try to discuss them one by one. Now, since we have here only two variables, x1 and x2, and the third variable is here y. So, one option we have that we can also make a three-dimensional plot, and so we try to go for a three-dimensional plot which is based on the wire. So, here I try to use means in the z-axis I try to use the drinking water variable, on y temperature, and on x-axis the humidity, and we get here this type of this 3D surface. Now, let us try to store it, and we will try to analyze it later. And similarly, there is another option here that we can have here a 3D surface plots. If I try to get the surface plot here, that will give us this type of surface. So, I am just trying to prepare the ground, and we would like to be confident that once I fit a linear regression model, we should be confident, yes, this is a situation where a multiple linear regression model can be fitted. Means obviously, when we have here more than three variables altogether, then the option of three-dimensional surface plot is not available. And then in that case, we have different options that we can take say three variables at a time, and then we try to combine all the individual inferences together, and finally the objective is to take one decision in terms of yes or no, that can we fit here a multiple linear regression model or not. Right. So, these figures are giving us a sort of confidence that yes, a multiple linear regression model can be fitted over here. So, now let me try to fit here a multiple linear regression model. So, you can see that in MINITAB it is not difficult, and it is a menu driven software. So, now here I am taking my response variable as drinking water demand, and I have taken here two independent variable as temperature and humidity. And yeah, means here we do not have any categorical variable which takes the values in terms of say 0, 1 or something like that. Now, let me try to explain what are the different meanings which are available to us. Right. So, here you can see that there is a possibility here that one can also add the interaction term. In multiple linear regression model, once we decide yes, two variables are interacting, then the observations on interactions are difficult to find in practice. So, what we try to do, we simply try to multiply the values of the two corresponding variables and we obtain the observations on interaction. So, but here in this case we are not considering the interaction term, so we ignore it. Okay. Now, if you see here, we have here different options. Now, I am setting here this confidence level for all intervals as 95. That means the level of significance alpha is here 5% or 0.05. Now, when I am going for confidence interval, I can have one-sided interval or two-sided interval. So we decide that in the case of linear regression analysis, we are usually interested in a two-sided confidence interval. So I give this option over here. Well, now when we want to find out the sum of squares, then there are two options that I can find out the adjusted sum of square or say sequential sum of squares. But in the case of linear regression analysis, what we have considered, we are interested in the simple sum of squares, or that is called here as say adjusted sum of squares. Right, adjusted had some other meaning, but that is beyond the scope of this lecture. Another option here is this Box-Cox transformation that we have not considered in this lecture, but this is a sort of transformation that is applied to the independent variables if y is not really related to x, but it is linearly related to some other power of x, something like square root of x or x square, something like this. So, but we are not considering here. So, we have just using here to define the level of alpha and the type of confidence interval and the type of sum of squares. Right. Okay. Since we are not using here the categorical variable, so coding is not important, and we are not using here the stepwise regression. Stepwise regression is another type of regression which we have not described in this course. Now, there is another option to have here the graphs. So, you can see here that there are different options: histogram of residuals, normal probability plot, residual versus plot, residual versus order. And you may recall that when we discussed the diagnostics for our multiple linear regression model, we had considered all the things. But in this case, I would be more interested in knowing whether the observations are originating from a normal distribution or not. And then I would try to have a plot for the residuals versus fit, so that I can decide for the presence of heteroscedasticity in my model. Similarly, for the residual versus order, we have a time series plot. So we can have all these things. Now, here if you see, now we have here three options that we can make these residual plots with respect to simple residuals that we have defined by epsilon I hat, or the standardized residual that we have defined say as di or say ri, say studentized residual or standardized residuals, and deleted residuals that we had defined as say e and I inside the bracket. So, here we would like to have here the regular one. Right, and then we would also like to see that what happens when we are going for a standardized one. Ideally, there should not be any difference. So, I will so in the first shot, I will try to obtain these plot for the regular residuals, and in the and then I will try to repeat this analysis, and I will obtain the plots for the standardized residuals. Okay. And now there is another option that I can have all the four graphics in one, but anyway that doesn't make any difference. Okay. Now another option is here results, that what type of results I would like to have. One thing is the method. Yes, we would like to know that what type of method we have used, right, like as least square principle or something like this. Then we would also like to know what are the outcomes of analysis of variance, and we would also like to know the model summary that consists of the statistics like R square, adjusted R square, press, and so on. And we would also like to store the values of coefficients, that is the values of beta 0 hat, beta 1 hat, and beta 2 hat. And we would also like to have a regression equation that is obtained after hitting the model. And we would also like to know the fits and diagnostic. If you remember, we had done different types of residual and different types of statistics like as HII, that is the ith diagonal element of hat matrix, deleted residuals, defits, and so on. Now I have here two options, that whether I would like to have this fits and diagnostic for all the observation and or say only for those observations which are found to be unusual. But since here we are learning, so we would like to see what happens to all the observation. And then there is another statistics what is here called as a Durbin-Watson statistics. We have not done this thing in detail, but still I would try to take its outcome and then I will try to explain you how to interpret it. Durbin-Watson test is a test to check the presence of first order autocorrelation in the data. That means in case if the data are affected by the time, then we have time series analysis, and in the case of time series analysis we try to test whether the observation have first order autocorrelation or something else. Right, okay. Now in case if you want, you can also store these results whatever you have obtained here, right. So this can be stored in the worksheet that is open here, and one may use it. So I will try to store it just to illustrate that how this actually works. So now once I go for this analysis, let us try to see what happened. So now you can see here that we have obtained here a normal probability plot. So we try to store it, and we have got here a plot between residuals and fitted value. Okay. So let us try to say store it. Now if you observe over here, this is the outcome. Here we have analysis of variance results in here, and here we have the details about the model summary, which is consisting about R square adjusted press and R square prediction. And similarly here we are getting the value of the regression coefficient, their confidence interval, variance inflation factor, and values for the t statistics. And here we are getting the fitted regression equation, and here there are different values of diagnostics, and since we had given that we would like to have this diagnostic for all the observation, so this is giving here say the fit, standard error of fit, confidence interval for the y hat, residual, standardized residual, deleted residual, HI, and Cook's D statistics. Here you can see, right, and this is available for all the 27 observations. And similarly the defit statistics is also computed here for all the observations. And at the end we have here Durbin-Watson statistics, and so we try to store these results separately, and then we will try to analyze it. But before we go for the further analysis, let us also try to obtain the this residual plots for the standardized case. So now I can choose here this option standardized, and let me do this analysis. So you can see here that we have now here these two graphics when the residuals are standardized. This is the normal probability plot, and this is here the standardized residual versus fitted value plot. Right, okay. So now we have stored all this information over here, and we would try to understand the interpretations and other things for these results. So you see, this is the matrix plot of the three variables y, x1 and x2. One can see here this is a plot between y and x1, and one can see here that it is showing us a linear trend, so there is no issue. Similarly, this is a plot between y and x2, and this is also showing here a linear trend. And similarly, this is also a plot between x1 and y, this is showing a linear trend. And similarly, this is also a plot between x2 and y, this is showing us a linear trend. Okay. Now, if you try to see here, this is a plot between x1 and x2. You can see here, ideally, we assume that x1 and x2 should be independent. So, we should have a scatter diagram like this one, but here you can see it is trying to show here a sort of linear relationship. So, let us see whether this is reflected in our regression analysis or not. But more or less this is giving us a surety that at least the relationship between y and x1 is linear, relationship between y and x2 is linear. So, we can believe that the relationship between y and x1, x2 jointly will also be linear. Okay. Now, these are the surface plots that we had obtained. You can see here that in this case, this is also showing a sort of increasing trend, and this is the same story here also. This is also showing a sort of increasing trend. So, these three-dimensional plot which are useful particularly in this example are also giving us confidence that a multiple linear regression model can be fitted in this case. Right. Okay. So, this is the same thing that we had obtained. It is in a bigger shape, and now after this we are going to discuss about the outcomes of a regression analysis. But before that, let me briefly describe some results so that it is easier for us to understand. You may recall that we had estimated beta hat, say x transpose x whole inverse x transpose y. So, in this case this is going to be like beta 0 hat, beta 1 hat and beta 2 hat, and the 3 cross 1 vector of these 3 values. And similarly, we have obtained the covariance matrix of beta hat, and which in this case will be variance of beta 0, beta naught, variance of beta 1 hat and variance of beta 2 hat. And on the off diagonal elements, this will be covariance between beta 0 hat and beta 1 hat, and covariance between beta 0 hat and beta 2 hat, and here the covariance between beta 1 hat and beta 2 hat. So, this matrix will look like this, and but our interest here is to go for its estimate. So, the estimates, and this value was obtained as sigma square x transpose x whole inverse. But here we are interested in the estimate of covariance matrix, so that we had obtained like this. So, this will be the estimated values, and this will be sigma square hat x transpose x. Okay. And you may recall that we had denoted for example, this as sigma square some matrix here C, where we said that variance of beta j and its estimator is given by sigma square hat C j j. J goes from here in case of 0, 1 and 2. Okay, so that is the symbol that we are going to use here, and when we are trying to find out the standard error, then standard error is say of beta hat j. This is simply the positive square root of estimate of variance of beta hat j. Okay. Then we also had obtained the confidence interval. The confidence intervals were obtained as say for say beta hat j. This was obtained as say beta hat j plus minus t alpha by 2 and minus k, and standard error of beta hat j. Okay. And for the test of hypothesis, when we are interested in testing the hypothesis S naught beta j is equal to 0, then the t statistics for the jth regression coefficient was obtained as beta hat j minus 0 divided by standard error of beta hat j, and this was following a t distribution with the n minus k degrees of freedom. Right. So, now you will see that these values which we have obtained earlier analytically, now they are being computed easily by the software. So, now let us try to understand here this outcome. I have divided the entire outcome into separate sheets so that we can understand them clearly. Right. Okay. So, let us go one by one. So, when we are trying to say here this coefficient is nothing but your beta hat vector. So, this is here beta hat 0, this is the constant. Constant means the estimator of intercept term, and the temperature means here the regression coefficient corresponding to the independent variable temperature x1, and similarly this is here the value of beta 2 hat which is associated with the second independent variable humidity. Okay. Now this is the standard error. So, these values are giving us the idea of standard error of different coefficient. So, this is standard error of beta hat naught, this is standard error of beta 1 naught, and this is the standard error of beta hat 2. Okay. The next column is about the 95% confidence interval. So, this is the lower confidence limit and this is the upper confidence limit for beta hat naught. This is provided by this expression T say alpha by 2 and with degrees of freedom n minus k, which is 27 minus 3, 24, and standard error of beta hat naught. And similarly, this is also a confidence interval for beta 1 hat obtained like this with alpha is equal to 0.05, and this is the confidence interval for beta hat 2. This is obtained at alpha is equal to 0.05 with 24 degrees of freedom and standard error of beta hat 2. Okay. So, these things give us this idea. So, before we try to go for the next column, let us try to understand what is the interpretation. The interpretation is that on the basis of given set of data, we can say that the value of intercept term here is 21361. This is the point estimate, and the confidence interval for beta naught is like this. This means the value of beta 0 is going to lie between 18871 and 23851. So, you can see that the point estimate is lying within the confidence interval. And similarly, the value of this beta 1 hat is indicating that the point estimate is 412.3, whereas the confidence interval is 316.2 to 508.5. So one can also see here that this is going to lie within the confidence interval, and the same thing is true for this beta 2 hat also, right. The physical interpretation of beta hat naught is the following, that when x1 is equal to 0 and x2 is also equal to 0, then the average value of y is going to be 21361, right. And similarly, the physical interpretation of beta 1 hat is that when there is a unit change in the value of x1, for example, in this case x1 is the temperature. So, when the temperature changes by 1 degree centigrade, then the change in the average value of y is 412.3. That means once the temperature changes by 1 degree centigrade, then the demand of water on an average increases by 412.3 thousand kiloliter. The question is why I am saying it increasing, because one can see here that the sign of beta 1 hat is positive. In case if this sign would have been negative, then I would say that the demand would decrease by 412.3 thousand kiloliter when the temperature changes by 1 degree. Okay. Similarly, here also in the case of humidity also, the quiz is trying to say that when there is a change of 1% in the humidity, that is it increases, then the average value of y changes by 77.5 units. That is, when there is a 1% change in the humidity, on an average the demand of drinking water increases by 77.5 thousand kiloliter, right. And these are the indicators like as standard errors. This is giving us an idea about the spread of beta 0 hat, beta 1 hat and beta 2 hat. Okay. Now we come to this column, t value. T value is about the test of hypothesis that H naught beta j is equal to 0. So, for example, this and here Tj is equal to beta hat j minus 0 divided by standard error of beta hat j. So, this value is beta hat naught divided by standard error of beta hat naught. This is the value of t statistics for the intercept term, and similarly this is also the value of beta 1 hat divided by standard error of beta 1 hat, that we had denoted by here say T1, and similarly this is also a value which is beta hat 2 minus 0 divided by standard error of beta 2 hat. So, these are the values of t statistics. Now, as I told you earlier that in order to test the hypothesis we have two options, either we can obtain the critical values or the tabulated values from the probabilities of t tables, or in software that is there is another option to use the p values. And we had learned that the result is that H naught is rejected if p value is less than alpha, that is the level of significance. So, here we have taken alpha is equal to 0.05. So, you can see here that the p value in all the three cases they are very, very close to 0. So, one can say that in this case all the three null hypotheses, that is H naught beta naught equal to 0, H naught beta 1 equal to 0 and H naught beta 2 equal to 0, all are rejected. So, that means none of the values beta 0, beta 1 or beta 2 is 0 or close to 0. This means the variables which we have considered here as a temperature and humidity, they are contributing in the model and they are helping in explaining the variation in the value of y. The last column is variance inflation factor. You may recall that we had discussed this diagnostic when we wanted to test the assumption of rank of x is equal to k, that means all x1, x2, xk are independent or not, and we had defined that VIF was equal to 1 over 1 minus Rj square, where Rj square is the coefficient of determination that is obtained by regressing the jth explanatory variable xj over the remaining k minus 1 explanatory variables. And if you remember, we had given the criteria that in case if VIF is lying between 1 and 3, this will be indicating that the independent variables are moderately correlated. And if it is more than 3, yeah, one can consider that they are highly correlated. Now, if you see here in this multiple scatter diagram, which I indicated here, you can see here that there is a linear trend here, sort of linear trend. So, one can see here that x1 and x1 and x2 are not really uncorrelated, but they have got a certain degree of linear relationship, and this is being indicated in this software here in this value 3.41 like this. Right. Okay. So, you can see that that our statistical analysis is also capturing this aspect. Now, based on this regression coefficients outcome, we can now formulate our fitted regression model as y is equal to, this is the value of beta 0 hat plus this is the value of beta 1 hat, this is x1 plus beta 2 hat times here x2. Right. Okay. Now, after this we have here some more model summary. This value here as S, this is nothing but your square root of sigma square hat. So this is, and sigma square hat was obtained by SS residual divided by degrees of freedom and minus k. Okay. And this is our here R square. R square was the statistics that was used to test the goodness of fit, and this we had defined as 1 minus SS residual divided by total sum of squares SST. So one can see here that this is 96.73. So one can be happier that the model which we have fitted is reasonably good, and essentially the variables x1 and x2 are capable of explaining say at least 96.73% variation in the values of y. Next quantity is here R square adjusted. You may recall that we had defined this quantity like R bar square, and this was defined as 1 over n minus 1 over n minus k times 1 minus R square. Right. So this is again say 96.46, which is again indicating that our model is nearly 96% good. And you will always see that R square is always greater than the value of R square adjusted, but usually in practice this difference is very small. Okay. The next here is press. The press was the statistics that was given by I goes from 1 to n epsilon I bracket whole square. You may recall that these epsilon I hats were press residuals. That means the difference between yi and say yi hat, which is obtained after deleting the ith observation. And based on this press statistics, we had defined the R square prediction, and which is obtained here by 1 minus press divided by total sum of square SST. So, and this R square prediction was the quantity that was helping us in deciding whether the fitted model can be used for prediction or not, and if used, how it is going to perform. So this value is here 95.81%. So so it is simply indicating that this model is nearly 95% good for prediction. Okay, so now let us try to concentrate on the other part, which is analysis of variance. So here degrees of freedom means is denoted by here df. So these are degrees of freedom, and yeah, here the software is computing another component, sequential sum of squares, and it is also computing the contribution of sequential sum of squares, which we have not covered in our lecture, but I will try to explain you its importance over here. What we have considered in our lecture is that we have obtained the sum of squares, which is denoted here as adjusted sum of square. So this is essentially, in our terminology, this is SS, the sum of squares, and this is in our terminology, this is mean squares, and this is the value of F statistics, and this is the p value. Now you can recall that we had divided the total sum of squares in the case of analysis of variance into two components: sum of square due to regression and sum of squares due to error, or sum of square due to residual. So this quantity here corresponding to this is giving us the value of SS reg, that is the sum of square due to regression. And this is the quantity here which is trying to give us the value of SS res, that is residual sum of squares. Now the software is also dividing this sum of square due to regression into two components, which is sum of squares due to regression due to the variable x1, and this is the sum of square due to regression due to the variable x2. Right. Yeah. And here also you can see this is the sequential sum of squares, which they have again divided it into two components due to x1 and due to x2, and they are using it in understanding the contribution of x1 and x2 in the regression sum of square. So here you can see this value is 91.54%. That means out of the two variables, temperature and humidity, temperature is contributing nearly 91.54% and humidity is contributing only 5.19%. Right, and the component of error here is only 3.27%. Right, the sum of squares will due to residual will remain the same as SS res. Right, so if you try to see even at these three values, they make sense. Whenever the temperature is high, usually the demand of water will increase, but if the humidity is also high, the demand of water also increases, but the rate of change is low. So that makes sense that the model which we are fitted and the values which we have obtained here, they are making some sense. Okay. Now this value here is mean square due to regression, and this value here is mean square due to residuals. Okay, and the same thing here they have obtained the mean square due to regression due to x1, and here they have obtained it mean square due to regression due to the second variable x2, and this value is the value of f statistics that was obtained as ms reg divided by ms res. So corresponding to this thing, the p value is coming out to be 0.00. Okay, and here this is the value of SST. This is the total sum of squares. Okay, and here you can see the degrees of freedom also. Here it is 2, which was equal to k minus 1, that is 3 minus 1, and this degrees of freedom was n minus 1. So this is 27 minus 1, and this was n minus k, so this is 24 degrees of freedom. Now if you recall what was our objective in analysis of variance, we were interested in testing a hypothesis like h1 beta 1 equal to beta 2 equal to 0. And here we have chosen alpha is equal to 0.05. So we can see here that the p value which we have obtained is close to 0.0, and this is smaller than alpha. So this implies that H0 is rejected. So this means beta 1 and beta 2 are not equal to 0, and correspondingly the variables x1 and x2 cannot be 0 simultaneously. So that is again confirming our outcome that we have got from the t values. Okay. So now this is a table where we have stored all the fits and diagnostics, and since we had given the option that we need it for all the observation, so now we have here 27 observation, and these statistics are available for all the 27 observation. So now I will try to explain it in our symbolic notation what we have used earlier in the lecture. The first column is drinking water demand, so this is nothing but our yi, and this is here the fit. That means this is the value of yi hat, and this is the standard error of fit. So this is essentially a standard error of yi hat, and yeah, I goes from here 1 to 27. Okay, and this is here the confidence interval for yi. Okay, and these are our ordinary residuals, and which we had denoted in our symbolic notations as epsilon I hat, that we had obtained as yi minus yi hat, or the difference between yi and yi hat. And these are our standardized residuals that we had denoted in our symbolic language as di, which was epsilon I hat divided by ms res. And this is our deleted residuals. and which we had denoted as epsilon I bracket hat. And this hi is in our notation is HII, and this is the ith diagonal element of hat matrix H. See here X transpose X whole inverse X transpose, and this is our Cook's D statistics. And so this in our notation we also have denoted it as here D, or these values are indicated by DI. Right. Now we try to look at the interpretation of HI. So you may recall that we had concluded that if HI is greater than 2k upon n, which was a sort of guideline, in our case this is 0.2, this would indicate that there are no leverage points. Right. So you can see here now in these values, none of the values is very close to 0.2 except here these values over here. Right, and then we had we will see later on also that these two values are quite far away from the fitted regression line. So this is also well captured by our defined statistics. Okay. Now we come to the interpretation of DIs, that is the Cook's D statistics. We had made a conclusion that in case if DI is greater than 1, then we would conclude that the data point is influential and it needs your attention. But you can see here that none of the value here is close to 1. So there is no question of having an outlier. And this was also indicated by our scatter diagram also, that there are no such influential point which are trying to drag the fitted regression line towards them. Right. Okay. Now we come to our next data. Here it is trying to give us the value of D fit statistics, and you may recall that we had defined the D fit statistic as a yi minus yi hat based on deleted residuals divided by sigma I square hat based on deleted residuals HII. And we had concluded that if absolute value of D fits is greater than twice of square root of k by n, which in our case comes out to be 0.66, then ith point warrants attention. So you can see here that here only there are two values here which are close to or greater than 0.6. So here we have to be a little bit careful, and that we will also see in the scatter diagram that 2 points at the end, they are going towards the downward direction. So this phenomena is again correctly captured by our statistics and our regression analysis. Right. Now the next value is about Durbin-Watson statistics. This is usually denoted by here D, and Durbin-Watson statistics actually test the presence of first order autocorrelation in the data. And here the decision rule is very simple, that if a D is smaller than 2, this indicates positive autocorrelation. And if D is greater than 2, this indicates negative autocorrelation, and if D is close to 2, this indicates no autocorrelation. So now here in this case you can see that the value of Durbin-Watson statistics is close to 2. So there is no autocorrelation of first order present in the data. Right. Now we try to analyze these values through our graphical procedures. So here I have plotted the values of yi and say yi hat, which I have obtained after fitting the model. One can see here that there is not much difference between the two values, right. So I can conclude that my model is well fitted, and even if I try to think it to use it for the prediction, it is not difficult to say that this model will continue further like this. Okay. And similarly, in the next graphic also I have plotted these yi and yi hat point by point. So you can see here, say from here to here, there is a sort of linear trend, and towards the end part over here, it is showing a sort of trend towards the downward, and that was actually captured in the D statistics and say residuals. Okay. So this is also confirming about the properties of the data, right. Now this is the normal probability plot, and the first figure is based on the normal probability plot based on ordinary residuals, and the second figure, this is the normal probability plot using the standardized residuals. So you may recall that we had concluded that if all such points which are lying over here as blue dots, if they are lying close to the line, nearly on a straight line, then we can be sure that the observations are coming from a normal population. And this phenomena is happening in both the cases, whether we are using the ordinary residual or the standardized residual. So this gives us an assurance that the assumption what we have made, that is correct, that our observations are originating from a normal distribution. Now these are the plot of residuals versus the fitted value. So here in the first case I have taken the ordinary residual, and in the second case I have taken the standardized residuals, and you can see that there is not much difference between the two, right. And from these two pictures we can conclude that all the points possibly they can be contained in a sort of horizontal band, and there is no pattern like outward opening funnel or inward opening funnel, or there are no indication of having a non-linear relationship. So from these two graphics we can conclude there is no problem of heteroscedasticity in the data, and our variance remains constant. Okay. Now I have considered here an example, and I have explained the complete statistical analysis whatever we have done in the earlier lectures in all details. Now please try to have a look at all these results and try to understand yourself that which of the quantity is indicating what and how it is computed. Once you know this thing, then you will have more insight into the data analysis, particularly in those situations when there is a problem. Because you are not going to deal in practice with 27 observations, but there can be several hundred observations. And then these diagnostics, these statistical results will help you in taking a decision that whether the fitted regression model is good or bad. You may not have an opportunity to look at the individual k-eta points, and you would like to inspect the individual k-eta points only in case of any problem. So I stop here, and in the next lecture I will try to take one more example to illustrate some further aspects of multiple linear regression analysis. Till then, goodbye.